Hello, welcome. In this short video, let us look at the derivation of CRB for a general Gaussian vector. That is, given the observation vector x that has a normal distribution with a mean mu of theta and variance and the covariance c of theta, that is the covariance matrix C is a function of the parameter vector theta, then we want to prove that element of the Fisher information matrix, that is ijth element of the Fisher information matrix I, that is the element in ith row and jth column, is given by the transpose of the derivative of the mean vector with respect to the ith component multiplied by inverse of the covariance matrix multiplied by the derivative of the mean vector with respect to jth component plus 1 by 2 multiplied by trace of the following product, that is C inverse of theta, that is inverse of the covariance matrix, multiplied by the derivative of the covariance matrix with respect to theta I, that is ith derivative of the covariance matrix, and then multiplied by the inverse of the covariance matrix, and finally the derivative of the covariance matrix with respect to the jth component. So this is the ijth element of the Fisher information matrix, that is element in ith row and jth column. So the vectors, that is the derivative of the mu of theta with respect to theta I and the derivative of the covariance matrix with respect to theta I can be defined as follows. That is, the derivative of the mean vector with respect to theta I is equal to the derivative of the first component of the mean vector with respect to theta I, and then second component, and so on up to the derivative of the pth component, that is the last component of the mean vector. Therefore, the derivative of the mean vector with respect to theta I is a vector that has these elements. So the derivative of this covariance matrix with respect to theta I is again a matrix whose elements are defined by the following structure, that is the element in the kth row and lth column of this covariance matrix is differentiated with respect to theta I, that forms the element in the kth row and lth column of the derivative matrix. Now let us look at the proof. So first we construct the log likelihood function of the vector x with the parameters theta, that is we want to construct the likelihood function, which is by definition 1 by 2 pi power n by 2 multiplied by 1 by the determinant of the covariance matrix C of theta power 1 by 2 multiplied by exponential of minus 1 by 2 x minus mu transpose C inverse x minus mu. Here mu basically represents or denotes mu of theta, and C represents or denotes C of theta. For simplicity, we basically ignore the parameter theta in the definition of mu and C. So the log likelihood function L of x, the parameter vector theta, is given by minus n by 2 log of 2 pi minus 1 by 2 logarithm of the determinant of the covariance matrix C minus 1 by 2 x minus mu transpose C inverse x minus mu. So this is the log likelihood function. Now the element of the Fisher information matrix I of theta ij, that is the element in ith row and jth column, is defined as expectation of the derivative of the log likelihood function, that is L of x of theta with respect to theta I multiplied by the derivative with respect to theta j of the log likelihood function. So this is the element in ith row and jth column. So first we have to determine the derivative with respect to theta I, that is derivative of the log likelihood function with respect to theta I, which is equal to the derivative with respect to theta I of the function defined here. That is, we basically rewrite the log likelihood function here. which is minus n by 2 logarithm of 2 pi minus 1 by 2 logarithm of determinant of c minus 1 by 2 x minus mu transpose c inverse x minus mu. So for simplicity, let us denote y as x minus mu, that is y as the difference between x and the mean vector. So we have the derivative with respect to theta I of minus n by 2 logarithm of 2 pi minus 1 by 2 logarithm of determinant of c minus 1 by 2 y transpose c inverse y. Now let us use the following matrix identities, that is, so the derivative of a logarithm of a determinant is clearly equal to 1 by the determinant multiplied by the derivative of the determinant with respect to the parameter. This is formula 1. And next thing we have to use is the derivative of a determinant with respect to a scalar parameter is equal to the determinant itself multiplied by the trace of inverse of the matrix C multiplied by the derivative of the matrix C. So this is equation or formula number 2. And finally, we also need to use derivative of inverse matrix is equal to minus C inverse derivative of the matrix with respect to the parameter multiplied by C inverse. This is equation or formula number 3. So we can use these three formulas to determine the derivative of this log likelihood function. So by using these three formulas, we have clearly the derivative of the first term is 0 since it is independent of theta. And for the second term, we have minus 1 by 2 1 by determinant of c into derivative of the determinant with respect to theta I minus 1 by 2 derivative of the product y transpose c inverse y. So by using the formula number 2, we clearly have the first term becomes minus 1 by 2 multiplied by 1 by determinant of c multiplied by determinant of c. Then we have trace of c inverse derivative of c with respect to theta I. So clearly these two terms cancel each other. And for the second term, we have minus 1 by 2 y transpose derivative of c inverse with respect to theta I multiplied by y. That is the first term. And for the second term, we have minus 1 by 2 multiplied by the derivative of y transpose with respect to theta. That is derivative of y transpose with respect to theta into c inverse y. And we have another term that actually matches with this term, which is minus 1 by 2 y transpose c inverse derivative of y with respect to theta I. Since these two terms are same, we can actually write them as 2 times this first term. And the derivative of the term y is clearly equal to derivative of y with respect to theta I is equal to derivative of x minus mu, which is minus derivative of mu with respect to theta I. We can use this formula for the last two terms of the derivative. So the first derivative of the log likelihood function becomes, the first term is minus 1 by 2 trace of c inverse derivative of c with respect to theta I. Second term is minus 1 by 2 y transpose derivative of c inverse with respect to theta I multiplied by y minus of minus plus, and there are two terms, so we have 2 times 1 by 2, which is 1, and then we have the derivative with respect to mu of theta I, derivative of mu with respect to theta I, and then c inverse derivative c inverse y. So these three terms, the combination of these three terms becomes the first derivative of the log likelihood function with respect to parameter theta I. Now we can write the element of the Fisher information matrix, that is I of theta ij, as the product of this derivative, that is minus 1 by 2 trace of c inverse derivative of c with respect to theta minus 1 by 2 y transpose derivative of c inverse with respect to theta y plus, there is a transpose here. So the derivative of the mu transpose with respect to theta I, C inverse y. We basically multiply this first derivative with the first derivative with respect to theta j, which is minus 1 by 2 trace of C inverse derivative of C with respect to theta j minus 1 by 2 y transpose derivative of C inverse with respect to theta j and multiplied by y plus derivative of mu transpose with respect to theta j C inverse y. So this is the element of the Fisher information matrix, the expectation of this product. Now let us write the square terms, that is expectation of minus 1 by 2 trace of C inverse derivative of C with respect to theta I with the minus 1 by 2 trace of C inverse derivative of C with respect to theta j. So that becomes minus of minus plus 1 by 4 trace of C inverse derivative of C with respect to theta I multiplied by trace of C inverse derivative of C with respect to theta j. So that is the first square term. And the second one is minus or minus plus 1 by 4 y transpose multiplied by inverse of C, derivative of inverse of C with respect to theta I, y multiplied by y transpose in C inverse derivative with respect to theta j multiplied by y. And the third term is derivative of mu transpose with theta I C inverse y multiplied by, we can rewrite this product as y transpose C inverse derivative of mu with respect to theta j. So we have y transpose C inverse derivative of mu with respect to theta j. And the next term is the product of the first term with the second and third terms, that is minus 1 by 2 multiplied by minus 1 by 2, that is plus 1 by 2 into 1 by 2 trace of C inverse derivative of C with respect to theta I multiplied by y transpose derivative of C inverse theta j y. And the next term is minus 1 by 2 trace of C inverse derivative of C with respect to theta I multiplied by the last term in the second bracket, that is derivative of mu transpose divided by theta j, that is derivative of mu transpose with respect to theta j C inverse y. And the next term is basically the product of the second term with the first term in the second bracket, which is minus or minus plus 1 by 4 y transpose derivative of C inverse with respect to theta I y trace of C inverse derivative of C with respect to theta j. And the next term is the product of second term and the third term, which is minus 1 by 2 y transpose derivative of C inverse theta I y derivative of mu transpose with respect to theta j C inverse y. And the last two terms are plus derivative of mu transpose theta I C inverse y minus 1 by 2 derivative of mu transpose theta I C inverse y trace of C inverse derivative of C theta j. And finally we have minus or minus. Finally the last term is minus 1 by 2 derivative of mu transpose with respect to theta I C inverse y multiplied by y transpose derivative of C inverse theta j y. So these 9 terms form the expectation of this product, that is the element of the Fisher information matrix. We can clearly see that the term here, that is this term, has an expectation of y which is clearly equal to 0, because since expectation of y is equal to expectation of x minus mu, and since expectation of x is mu, this is equal to 0. So this term, and similarly the third moment, that is expectation of, that has 3 y terms, that is this term and the last one, are gone because that is also 0. That is, since the first and third moments of y are clearly 0, So we lose these 4 terms. That is, since the first moment and also that is y transpose y is equal to 0, or any expectation that has 3 y terms is clearly 0. So the terms, the 5th term, 7th, 8th, and 9th terms are zeros. So we are left with only 5 terms. And also the term number 6 exactly matches with the term number 4. So they can be combined into a single term. Note that this term is similar to this term. And when you take expectation, they will eventually have the same value. So we can rewrite the expectation as follows. The Fisher information matrix element in ith row and jth column of the Fisher information matrix is defined as, it will be equal to 1 by 4 trace of C inverse derivative of C with respect to theta I multiplied by trace of C inverse derivative of C theta j. That is the first term. Here. And the second term is expectation of this product, which is plus 1 by 4 expectation of y transpose derivative of C inverse with respect to theta I into y transpose derivative of C inverse with respect to theta j and y. So that is the second term. The third term is given by the expectation of this product, which is plus derivative of the mu transpose with respect to theta I C inverse expectation of y into y transpose into C inverse derivative of mu with respect to theta j. And the last term is given by 2 times this product, which is 1 by 2 times the trace multiplied by the expectation of this product. It is plus 1 by 2 trace of C inverse derivative of C with respect to theta I multiplied by expectation of y transpose C inverse theta j y. So these 4 terms basically constitute the element of a Fisher information matrix. So the first term does not change, so it is still 1 by 4 trace of C inverse derivative of C with respect to theta I multiplied by trace of C inverse derivative of C with respect to theta j. And for the second term, we are going to use the matrix identity defined as follows. That is, expectation of the product defined as y transpose A y into y transpose B y is equal to trace of A into C trace of B into C plus 2 times trace of AC BC. That is, the product is A C B C, where C is equal to expectation of y times y transpose. And in our problem, it is clearly the case. That is, C, the covariance matrix, is the expectation of the product y times y transpose. So the second term becomes plus 1 by 4. The matrix A is clearly equal to the inverse of the covariance matrix, the derivative of the inverse of the covariance matrix. So the first element is trace of the derivative of inverse of covariance matrix multiplied by C, which is again C, multiplied by trace of, again B is also the derivative of inverse of covariance matrix with theta j. So it is derivative of C inverse with respect to theta j multiplied by C. And the second term is 2 times the trace of AC into BC, which is 1 by 4 into 2, that is 1 by 2 trace of the inverse of covariance matrix with respect to theta I into C inverse of the covariance matrix, derivative of the inverse of covariance matrix with respect to theta j into C. So that is the second term. These 2 terms constitute the expectation of the second term. And next we have plus the derivative of the mu transpose with respect to theta I C inverse into C, that is expectation of y into y transpose is C, and then we have C inverse derivative of mu with respect to theta j. The last term can be rewritten as plus 1 by 2 trace of C inverse derivative of C with respect to theta I multiplied by, and this product can be rewritten as expectation of trace of y into y transpose derivative of C inverse theta j. That is, we basically use the matrix identity y transpose into D multiplied by y is clearly equal to trace of y transpose into D. So by using this formula, we have this result. And since expectation of y times y transpose is clearly equal to C, next by using the formula, that is derivative of C inverse with respect to theta I, that is the formula 3, this formula, that is derivative of C inverse with respect to theta I is minus C inverse derivative of C multiplied by C inverse. So by using this formula, in this term we have, so we just write this term as the first term, we get plus 1 by 2 trace of C inverse derivative of C with respect to theta I multiplied by trace of, so expectation of y into y transpose is C, and the derivative of C inverse is minus C inverse derivative of C with respect to theta j into C inverse. And then by combining the first term with the second term, since they are actually same, we have plus 1 by 2 trace of C inverse derivative of C with respect to theta I multiplied by trace of C inverse derivative of C with respect to theta j. And the remaining two terms are basically the product of the derivative of the mean vector mu with C inverse, and since these two cancel each other, and the last term is derivative of mu with respect to theta j. So that is the next, plus derivative of mu transpose with respect to theta I C inverse derivative of mu with respect to theta j. And the next term is of course plus 1 by 2, that is this term, the derivative of the trace of C inverse derivative of C with respect to theta I C inverse derivative of C with respect to theta j. And clearly the first term will cancel with the second term, since this is equal to inverse of the additive inverse of the second term. That is, this is equal to minus 1 by 2 trace of C inverse derivative of C with respect to theta I, and this is trace of derivative of C theta j into C inverse, and trace of the product derivative of C with respect to theta j into C inverse is same as trace of C inverse into derivative of C with respect to theta j. So this term and the second term will cancel each other. This plus 1 by 2 trace of C inverse derivative of C with respect to theta I multiplied by trace of C inverse derivative of C with respect to theta j. So these two terms cancel each other, and therefore we are left with the product derivative of mu transpose with respect to theta I multiplied by C inverse derivative of mu with respect to theta j plus 1 by the trace of the product, that is C inverse derivative of C with respect to theta I C inverse derivative of C with respect to theta j. So clearly the element of the Fisher information matrix, that is the element in ith row and jth column, is equal to the sum of these two terms, that is mu transpose with respect to derivative of mu transpose with respect to theta I C inverse derivative of mu with respect to theta j plus 1 by 2 trace of C inverse derivative of C with respect to theta I, and again C inverse derivative of C with respect to theta j. This is the final result. Thanks for watching.